Hi everyone, I'm Dr. Surjit Singh. Today we'll talk about the Leetcode problem word ladder. Welcome to my video. Let us begin. In this problem, we are given a starting word from which we are to reach an ending word in a series of single character switches using words from a given list. All words must be of equal length. In this method, we will set up a graph of all the words in the given list that differ by one letter. Then we will use this graph to solve the problem by employing the BFS approach. We will transform hit to cog using these six given words. Each word has same length equal to 3. The result is 0 if length of words is 0 or if end word is not in the list. Let us set up the required graph. We define a dictionary and process the words in the given list one by one. First word is hot. It has three characters. One by one, we replace these characters with dash. In the first iteration, we get dash OT. We save hot against this generic word in the dictionary. Next iteration gives H-T, which is also added to the dictionary. In the next iteration, HO dash is added. Next word is dot, which gives three generic words as shown. Dash OT is already in the dictionary. We add a new entry in the list against it and add the other two keys in the dictionary. Dog is added to do dash and we add two new entries in the dictionary. Next three words complete the dictionary as shown. Graphical representation of first line of dictionary is that hot, dot and lot are connected with each other by a single switch. Next three entries in the dictionary are singletons. Dot and dog are linked with each other. Dog has two more links, namely with log and cog. Finally, lot and log are also connected. Cycles are present in this graph, so it is not a tree. To avoid repetitions, we define a list named visited with begin word as its first entry. Cog is the end word in the graph. We use a queue to manage BFS. The begin word at level 1 becomes the first tuple in the queue. We use while queue to start BFS. In every iteration, we pop out one entry from left of the queue to follow the first in first out basis, and they become current word and level. We start a loop to obtain three generic words of hit. First generic word is dash IT. It is not present in the dictionary, so next for loop is skipped. Next generic word is H-T, for which list has only one word, hot. Hot is not the end word. We add it to visited list and also add it to the queue for level 2. The loop terminates. We clear the list for H-T. This helps in preventing futile repetition in future cases. Third generic word is HI dash. This is not present in the dictionary, so the iteration is skipped. We move the queue further. Hot is extracted from the queue and it becomes the new current word. Its first generic word is dash OT. It is present in the dictionary which has three words in its list. In the first iteration, word is hot. It is not the end word, but it is present in the visited list, so we move to the next word. Next word is dot. It is added to visited and also to the queue at level 3. Next word is lot, which is also added to visited as well as to the queue. After processing all the words of dash OT, its list is cleared. Next generic word is H-T, but its list in dictionary is empty. Third generic word is HO dash. It has only one word hot in the list, which is already in the visited list. So we clear this list without any processing. All the words at level 2 are processed, and now we will process the word dot at level 3 by extracting it from the queue. First generic word of dot is dash OT, for which the list is empty. Next generic word is D-T. It has only one word dot, which is already visited. So we clear this list. DO dash has two words. Dot is already visited. We now add dog in its visited list and in the queue. We clear the list for DO dash. Now we extract lot from the queue, which becomes the new current word. Its first generic word is dash OT, for which list is empty. Next is L-T. Its word lot is already visited. We clear its list. Next is LO dash. Lot is already visited. We add log in visited list and queue and clear the list. We now extract dog from the queue. Dog becomes current word. Its first generic word is dash OG, which has three entries, out of which dog and log are already visited. The third word, cog, is the end word, so process is terminated and 5 is returned as the result. Note that we have been adding and removing words in the queue. We break out of the loop only when the end word is encountered. In case all the words in the queue are processed without coming across the end word, the return value is 0. In BFS approach, all nodes of a particular level are processed before shifting to the next level. This ensures that the length of the path is the shortest. For n words of length m each, time complexity is of the order of m squared n. Because of each word in the list there are m generic words, there are m times n iterations to create the dictionary. Further, formation of each generic word takes time of the order of m. In the worst case, we may have to traverse all the words of the list. Each of the n words has m generic words. So in the dictionary, there are m times n entries, each of the size m. So space complexity is of the order of m squared times n. This is an improvement over the previous method. We start queues from both beginning and end and move the queue which has lesser entries. This way we cross over to next level in lesser number of trials. Process stops where the two sides arrive at a common node. In this solution, we define class level variables length and generic dictionary. Length is 3 in this example. We define a function visit node which we will discuss in a bit. We will now write function ladder length based on bidirectional BFS. We check that length of the word is not 0 and end word is present in word list. We set up the generic dictionary as before. We define two lists. Q begin list has begin word and Q end has end word. We also define two dictionaries. In visit begin, begin word has value 1 and visit end has end word with value 1. We define ans equal to none and we start a loop that runs while neither of the queues are empty. In order to get new value for ans, we call the function visit node for the queue which has lesser entries. Three variables will acquire new names in the function as shown. In the present case, QBegin becomes Q in the function. Inside the function, we define variable QSize which gets value equal to the length of the queue, which is 1. Presently, queue has only one entry, so the for loop will run once only. In this iteration, the word hit is popped out of the queue and it becomes current word. In the nested for loop, we generate its generic words. First is -it. It is not in the generic dictionary, so the next for loop is skipped. Next generic word is h-t. Only word present in its list in the generic dictionary is hot. Had it been present in other visited, the problem was solved as the two paths join. However, it is not present in other visited. It is also not in visited, so it is added there with value equal to 2 and is also added to the queue. Third generic word is hi dash, but it is not in the generic dictionary. All loops terminate without any solution, so we return none to the calling function. All local variables are cleared and the function parameters acquire their original names. The returned value is stored in ans, which remains none. Both the queues are not empty, so the loop continues. We notice that all changes are similar to the previous method. In the next cycle, hot is extracted from queue begin, while dot and lot are added to it and also to visited begin. Note that queue end is now shorter than queue begin, so in the next cycle, cog is extracted from queue end. In this call, visited end will become visited and visited begin will become other visited. Dog is added to both queue end and visited end. Once again, queue end is processed. Its neighbor dot is present in other path, so the process is terminated and 5 is returned. Ans becomes 5 this time, which is not none, so it is returned as the final answer. This takes lesser time as we do not have to process lot at any stage. Time complexity is same as before. However, the number of iterations can be lesser because we separate the queue into two parts. We know that number of entries in a BFS queue increases suddenly if its number of levels become very large. Therefore, in this case, the execution time can be much less. Memory used in forming the generic dictionary is the same, so space complexity remains unchanged. Thank you all for watching the videos. Please stay tuned for more such videos and please subscribe to my channel.